Hello and welcome back. The purpose of this video is to derive the ideal gas law. And I know you see a lot of stuff written on the board. We're going to go through all of it slowly. Please don't be overwhelmed. There are some assumptions that must be made to use the ideal gas law. And so we're going to use them for our derivation. The gas molecules must be able to be considered as hard spheres, and their motion is frictionless. In addition, all collisions must be elastic. That's collisions with the molecules, other molecules, and also with the container walls. The distance between the molecules is large compared to their size. Molecules move in random directions with a distribution of speeds. And there are no attractive or repulsive forces exerted between molecules. So the only forces being exerted by one molecule on another is going to be through an elastic collision. So the collision with the container walls are elastic. Let's consider a cube, of which I've just shown the front face of it. So 2 dimensions of that cube. The cube has dimensions L, so that means all of the dimensions are L, its length, its width, and its depth are all L. And it has N, capital N molecules enclosed within this volume, and the masses of all of the molecules are the same. So the mass of molecule 1 is the same as the mass of molecule 2, et cetera, et cetera. And it might be worth pointing out that I can write the total volume as just L cubed. The length times the width times the height. It's a cube, so all those dimensions are the same. So, starting off with this concept that the collision with the container walls is elastic, we're going to use Newton's second law and say that the force being exerted by the container walls, so this is by the container wall, is going to be equal to the change in momentum for some particular molecule that we're going to look at, divided by the time over which it takes to collide with the wall. So we can see here is our molecule 1, and it is moving to the left, and I'm using the standard coordinate system. So there's molecule 1, so it has mass m1. And we see that we can write the change in its momentum as its final momentum. So it's going to hit the container wall and it's going to bounce back. So it's going to be traveling in the other direction upon reflection. So the final momentum is going to be m times a positive vx1 minus the initial momentum, and the initial momentum is going to the left, so it gets a negative sign m1 v1x. So this is conservation of momentum in that it has the same momentum before the collision as after the collision. That says it's a completely elastic collision divided by the time. So the force then being exerted by the container wall on the molecule is 2 m1 vx1 squared divided by delta t. There's just 2 of these terms in the numerator when I distribute that negative sign. In addition, between collisions, imagine this molecule just traveling back and forth. It's going to hit this left side every 2L over vx1 as far as time goes. So it's going to be traveling a distance 2L with this speed vx1 in the time between collisions. So I can write delta t then as the distance over that speed, and so then substituting that in allows me to now write the force exerted on the container wall and by the container wall. Newton's third law pair is going to be this change in momentum to m1 vx1 divided by the time, and the time can be written as the time between the collisions, 2L over Vx1. So I've taken this equation and now substituted in for delta t, and you can see that the 2's are going to cancel, and this Vx1 is going to flip up into the numerator, and so this can be written as m Vx1 squared over L. So the total force felt by the container wall is going to be the sum of all of the molecules. We just looked at one molecule, But this wall right here is going to feel a force from the second molecule, the third molecule, the fourth molecule, all the way up to the nth molecule. So we're going to have these speeds associated with these different molecules, also subscripted. So here's the change in momentum for molecule 1 divided by L, change in momentum for a molecule 2 divided by L, etc., all the way up to the nth molecule divided by L. Notice that since the masses are all the same, I'm just going to write that as M, and I'm factoring out the L that is also common. So the M is common and the L is common, and what I have then is just the sum of the squares of the speeds. Now what we're going to do is we're going to define the average speed in the x direction squared. So this is Vx squared averaged as the sum of all of these speeds squared of all of the molecules divided by the total number of molecules. This gives me the average squared speed. Notice that these are not the same. Vx squared average is not the same as Vx average squared. In fact, Vx average squared is going to be 0. There's as much probability of a molecule traveling to the left with the same speed as a molecule traveling to the right, and those two would average to 0. So what we've done instead is we've squared all of those speeds first to get rid of any negative signs, then we find the average. So now I can multiply by n on both sides, and notice when I do that, now I have Vx1 squared plus Vx2 squared, etc. Well, this is the stuff that's in the parentheses over here. So I can substitute this left-hand side for this stuff that's in the parentheses, and so that's what I do. The force exerted by the container wall then is going to be m divided by L, and now substituting in this parentheses right here is the left-hand side. This is m Vx squared averaged. Now, the molecules' velocities are all random. Therefore, I can say that the x velocity squared and averaged is equal to the y velocity squared and averaged is equal to the z velocity squared and averaged. Because notice, I just am looking at the force being exerted by the container wall, which can only be in the x direction. But this molecule could also have a y component or a z component that is going to be unaffected by this container wall. The container wall can only exert forces along the y dimension. Since the molecules' velocities are all random, on average, then the x component, the y component, and the z component squared and averaged are all the same. And the total velocity squared and averaged is just the sum of all of the individual axes squared and averaged. So Vx squared averaged, Vxy squared averaged, and Vz squared averaged. So then I can write Vx squared averaged as the total velocity divided by 3. In other words, I can write this is Vx squared averaged and this is Vx squared averaged, so that I have 3 Vx squared averaged on this side. And if I isolate Vx squared averaged, then I get the total velocity divided by 3. In addition, the force being exerted on the container wall is yielding a pressure over the area. And the area of the wall is just L squared. So I can substitute also the force exerted on the wall as pressure times length squared. So I'm going to substitute in the left-hand side of this equation as PL squared. And now I'm going to take the right-hand side of the equation, which we have right here, and I'm going to write that as m over L times n, and then Vx squared average now is going to be the total velocity squared and average divided by 3. Now notice I've got an L in the denominator here and an L squared on the other side of the equation in the numerator. So I'm going to multiply both sides by L, and L cubed then, which I'll have on the left-hand side, is the volume of this cube. So I can write pressure times volume now on the left-hand side. And what do I have left? Well, here's this 1/3 I'm going to put out in front. I've got m left and I've got n left. And then I've got the velocity squared and averaged as well. Remember that the average kinetic energy can be written as 1/2 mv times the average velocity squared, or sorry, the velocity squared and averaged. So I'm going to take this expression and I'm going to solve for mv squared and averaged, and I'm going to plug in 2ke for that. So you can see here I've got mv squared averaged. I'm going to substitute in 2ke average. So this is the pressure times the volume now is 2/3 times the number of molecules times the average kinetic energy. Now from calculus and statistics, we can show that the average kinetic energy is actually related to temperature. In 3 dimensions, it's 3/2 K, where K is Boltzmann's constant, you can look it up in the textbook, times the temperature. Temperature must be in units of Kelvin. So the average kinetic energy is actually just a measure of the temperature of the molecules, or vice versa. The temperature that we read on the wall in the room is just a measure of the average kinetic energy of the molecules in the room. So I'm going to substitute in now then for Ke as 3/2 kT, and when I do that, I get that P times V is 3/2 N times Ke average. Substituting this in, you see that when I put in 3/2 kT, the 2/3 and 3/2 are going to cancel, and I'm going to be left with PV is equal to N kT, where N is the number of molecules, K is Boltzmann's constant, and T is the temperature in Kelvin. So this is the ideal gas law. Notice using Avogadro's number, I can instead use the number of moles and the gas constant. So Boltzmann's constant and the gas constant are related via Avogadro's number. So we can also express the ideal gas law, if we would prefer, as PV equals nRT. So this is piv nert and piv nict. Little n is the number of moles, big N is the number of molecules. When you're using the number of molecules, you use Boltzmann's constant. When you're using the number of moles, you use the gas constant. So I'm hoping you followed this derivation. We've studied enough physics where we are able to apply these concepts, and I'm hoping you don't need to regurgitate this, but I'm hoping that you understand the steps that we went through and ask questions if you didn't. And we'll see you next time. Thank you.